Is there a link between confidence intervals that we looked at in the last chapter and hypothesis testing that we're looking at in this chapter? Well, the answer is yes. Now, we had bootstrap samples or distributions that we looked at in the last chapter, and randomization distributions we looked at in this chapter. Now, bootstrap is our best guess at the distribution of the sample statistic. And well, that's the same thing for our randomization distribution, but we're assuming that the null hypothesis is true, which means then it's centered around your hypothesis value, where with Bootstrap, it's centered around your sample statistic. We then do our simulated sampling of our population by resampling the original data. And this randomization distribution does kind of the same thing, but assuming your null hypothesis is true. So the main thing here is randomization distributions assumes that your null hypothesis is true. Bootstrap doesn't. Now, for which one of these graphs down here on this situation, which one is a bootstrap distribution? Well, your bootstrap is always centered around your sample statistic. So that's going to be the one on the left. So what about this situation? Which one is your randomization distribution? And your population parameter is 1/2. Keep in mind, if you divide these two numbers here to get your proportion here, it's about 0.7. So which one of these down here would be your randomization? If it was a bootstrap, you would have it centered around 0.7 because that's what we had up here for our sample statistic. But randomization is centered around your population parameter, which was 1/2, so that would be A. So creating a bootstrap for our average body temperature from our original data that we had looked at before was this here. Bootstrap, once again, is centered around your sample statistic. Now, basically, if we want to do our randomization distribution, we'd want to go ahead and take our graph from back here, our bootstrap. We'd want it not to be centered around 98.26, but 98.6, which is a 0.34 more. So we'd really want to go ahead and take our distribution back here, take all these points, add 0.34, because that's what you have to add to get this up to 98.6, to all these points, and it moves that over to your 98.6, and it's centered around there. So looking at this, these two distributions are identical in shape, except where our center is. The bootstrap is centered around our sample statistic, while the randomization distribution is sampled or centered around our hypothesis, our null value, our parameter from our population. Bootstrap is centered around your statistic from your sample. For the most part, they're both the same, except we're going to just take your bootstrap and shift it over to get your randomization distribution. So, what is the link between confidence intervals and hypothesis tests? So if we have a 95% confidence interval and our parameter, meaning our null hypothesis, is within that 95% interval, then our two-tail test, meaning the not equal to, would not reject the null hypothesis at a 5% level. By the way, the 95 and the 5% have to add up to 100%. So if this was a 90%, then our significance level would be 10%. If our confidence interval was 99%, then our significance level would be 1%. But basically, if your confidence interval contains your null hypothesis, we don't reject. However, if your confidence interval misses it, as in if that parameter, your null hypothesis, is in one of the tails outside of your 95% confidence interval, then we would reject it because your p-value would be less than alpha at a 5% level and make it statistically significant. So if you are within the 95, if you're within the confidence interval for your population null hypothesis, you don't reject. If you're not in that interval, then you do reject. Confidence intervals give a plausible range of values for what you would expect for your population parameter, where your hypothesized value is not within your confidence interval and it's outside, you would not expect it outside the confidence interval, you would not expect it and it should be rejected. If the null hypothesis is within the confidence interval, it's within the plausible range of values and should not be rejected. So looking back at our bootstrapping for a 95% confidence interval for our body temperatures, we had 98.05 degrees to 98.47 degrees. Now, 98.6 is not in that interval. It's outside of it, so it's outside the reasonable value, so you would want to reject your null hypothesis if you were doing a two-tail test. Now, does every child need both the father and mother? Well, our proportion from our 2010 survey, our 95% confidence interval, was that proportion was 0.487 to 0.573. Well, your null hypothesis would be 50% or 0.5. Now, 0.5 is within that plausible range of values of your confidence interval. It's in that confidence interval, so you would not reject your null hypothesis because it falls within that confidence interval. However, back in 97, your confidence interval that we had was 0.533 to 0.607. Now, zero point 0.5 is not within that interval. It's not within the plausible range of values for that confidence interval. It's outside of it, so then you would reject your null hypothesis. So confidence intervals are really useful when you're looking for a range of values to estimate your population or an estimate of your population. Well, hypothesis tests and your p-values are useful if you're trying to just make a test and say, yes, this is significantly different, or no, it's not statistically significant or significantly different. So confidence intervals give you a range of plausible values, while your p-values, your test, gives you the strength against your null hypothesis. So for each one of these situations, do you think it would be best to do a confidence interval, a hypothesis test, or it doesn't make a difference because it's not statistically relevant to what we're looking at? So do the majority of adults riding a bicycle wear a helmet? I would say this one is a test. We want to know, yes, is this true, or no, is this not true? The second one, how much more do adults who played sports in high school exercise than adults who didn't? So here we're looking for how much more. We're looking for a range of values about how much more. So this would be a range of values, and that's what you get out of a confidence interval. Down below, on average, there are 23 players on the 2010 Olympic hockey team, and that they were older than 23, or older than the 23 on the 2010. Well, it's really just an observation that, yes, that is true. Or no, that's not true. It's not really statistically significant to look at. There's no real reason to investigate that. It's just an observation. So something can be statistically significant, but not practically significant. So a small sample size can make even large differences in effects not significant. Or the kind of the other extreme, a large sample size will make even small differences significant. Just because it's statistically significant does not mean it's really practically significant. So consider this. We have a weight loss program with 10,000 people in it, and it's an experiment. Well, 10,000 is a pretty big sample size. Now, the difference in weight loss was only a half a pound in a randomized experiment, but it was still found to be statistically significant. But if it's throughout a year, is a half a pound difference throughout a whole year really practically significant? No, it's not. Now, we're going to shift gears and talk about something else. So we're going to continue that on the next video.